So we'll kick off the presentation. This is regarding the KMC Conquest airflow measurement system, otherwise known as Genius Ventilation. Now, I know that everybody really wants to hear Scott talk about how awesome everything is and the technology that's gone into this revolutionary product, but I'm holding the clicker, so you're going to listen to me talk about a bunch of fluff before we get on to the real meat and potatoes, okay? Everybody in here knows KMC. We've been in business 50 years. We can't tell you how much we appreciate each and every one of you as partners. The reason that we are discussing our airflow measurement station and why we've invested in bringing this product to market, you know, it's really had a spotlight shown on it over the last 18 months relative to COVID. But even before that, you know, there's been numerous studies that directly correlate the indoor air quality to occupant performance. And, you know, just a stat that I read before coming in to talk to you all was that poor air quality results in $150 billion of illness-related costs per year. $150 billion. Correct. Thanks, Harold. And, you know, if anybody had a chance to attend the specifying indoor air quality presentation, one of the big things that we talked about was educating your customer, you know, getting with your client and talking about, like, are you meeting code minimum? Do you care about indoor air quality? You know, what's really on their whiteboard? What's on their dashboard, and where are they going with it? And there's a lot of confusion. I mean, the best practices that are spelled out from the CDC or from ASHRAE are around filtration, you know, purification, sterilization, whether it's UV or bipolar ionization. But the one thing that everybody seems to come back to as the number one mitigating factor of anything related to illness is ventilation, fresh air ventilation. And there's also all of these studies that equate proper ventilation rates to improve performance, which is why we're here. This is why we're talking about this. So over the last few months, you know, I don't know if anybody has seen the videos from J-Lo, you know, where she's talking about, you know, the well standard. Look for the well standard on the buildings that you're going into, or your you know, your hotels. And J-Lo's on that you know, commercial too. A bunch of real rocket scientists. But, you know, they've got a platform, and people pay attention to that. And, you know, it's becoming more and more on people's minds that are beginning to reoccupy buildings. And we've seen a lot of reluctance from, you know, whether it's the teachers' unions or, you know, workers' unions to actually reoccupy buildings. And, you know, as a manufacturer, well, we got a lot of cost involved in maintaining our building, and that's where everybody needs to go to work, and we want to see people in there and be confident in the building itself. So the other thing that we've seen is, you know, tenants, like, you know, people that are, whether they're renting, are they in a you know, mixed use or you know, mixed family space where it's condos or whatever the case may be, they want to be assured that, you know, the landlords, people that own the building, are taking their health seriously. So again, you know, the industry is really focusing on you know, maximizing health and occupant wellness, and you know, this is why measuring outside air, measuring ventilation rates is incredibly important right now. Another stat I'll throw at you all is employers have seen an 11% increase in worker productivity after cleaning the indoor air. So again, the major aspect of any one of the algorithms for producing an indoor air quality dashboard is ventilation. So, you know, with all of this focus on ventilation, you know, why hasn't customers necessarily, you know, taken to it like duck to water or fish to water, whatever you want to use from an analogy perspective? Well, you know, the problem is there's a lot of confusion in the marketplace. The technology that's available isn't applicable across the board. You know, how do you measure, you know, ventilation rates on a unit ventilator? How do you get in there and work on that thing? So, you know, we see that as a gap that we can help to address with our airflow measurement system. Additionally, you know, who in this room has worked on or designed a system where you're using like an Ebtron sensor, and let's say that you got, just the perfect mechanical system laid out, 4 duct, diameters downstream or upstream and 10 downstream, and boy, that thing's just going to meet specifications, and going to work like magic every time. Who's ever had that experience? Once. Congratulations. Time to retire. Yeah. Yep. Yeah. It's a mess. It's confusing. So, there's a high cost of installation. It's complicated. You almost never meet those exact specifications from an engineering standpoint. So, you get inaccuracy. You get, fluctuations in readings. You get, mixed performance. You get, nuisance calls from either the building owner or, additional callbacks for a balance, testing and balancing contractor to come out. Hey, this, what's on this dashboard doesn't match, what we're seeing in our building automation system, et cetera, et cetera. So, other things that could affect the performance of one of those sensors is, do they have it mounted to measure outside air? Like, are they putting it on a hood scoop? You get, all kinds of rain, accumulated dust, feathers, chicken crap, whatever the case may be. So, there again, just a lot of deficiencies in what we see on the market, and these are all aspects that we look to address with the airflow measurement system. So, here's the elevator pitch, guys. In comparison to your traditional probe-style airflow measurement systems, give you 1-point measurement. Our airflow measurement system provides data on your supply air, your outside air, and your return airflow. So you're not only able to monitor all of that information with the airflow measurement system, you're also able to control the equipment because it's based off of one of our KMC Conquest controllers. The measurement is based on characterized damper performance. So we'll go through a slide in a little bit here where we'll show you, essentially how this is laid out on a piece of mechanical equipment. If you want to go to the demo room and actually see, the components, if you haven't been there already, you can take a peek at that. But effectively what we are doing is we are correlating the actual position of an outside air damper to airflow rate as measured at the supply fan. So we're measuring filtered air as opposed to air that's exposed to any type of ambient conditions. And what we are giving you is accurate, repeatable results on any type of equipment without mechanical limitations. So this is kind of the magic behind the scenes. All of the, go ahead. Mm-hmm.
It's almost near across. If it's strictly one side, if it's double sided dogs.
I'm going to have Scott or Eric answer that.
So if you got both sides, do you have to go both sides for measurement?
Well, typically,
or you just take off one side and then double it.
You can do that, and we found that to be effective. Is it proper according to ASHRAE standards? Probably not, but it is effective and accurate if you're just measuring one side and you put together the two areas. But if that's impossible for you to do, going downstream a duct and using some pitot arrays, which we don't have any.
No, we do. We've got that
in the demo room. Yeah.
Our grinding room.
Measuring it downstream is perfectly acceptable as well. The best way to get the supply airflow reading that you can get is what we're looking for. But it's also the easiest way and most.
I want to run that in a couple instances, but they were the most compact rooftop I've ever been in. Mm-hmm. And you could barely get at the one side, and there's no way now you're going to get the other side without pulling the fan and then.
Right. Yeah. So in that application, for ease of installation, you can measure one side, but you have to add the other side as part of the area. The best thing that you need to do though is have it calibrated by a tab agency, so you know that you're delivering what air, he says is there.
So you're measuring out the fan using the transducer controller. And then you're using the damping position indicators to do the math to calculate, well, based on this damping position, we're bringing in X number of outside air, this much return, and therefore this is the amount of air that should flow through the system for each direction. Okay.
Correct. This is just a sample picture of an installation. I'm skipping ahead a little bit, but I'll come back to this item. I'm sorry, I don't know your name.
My name's Mark.
Mark. So as Mark points out, that's effectively what we're doing. We're correlating the damper position and the airflow measurement as taken at the fan to give us outside air, supply air, and return air flow measurements. And that's a practice that's commonly utilized in the testing and balancing industry. Scott utilizes the mixed air temperature equation, ASHRAE standard 111, on a routine basis in his testing and balancing business, and we're pleased to have him as a technology partner to help in delivering this product and bringing it to you all. So the components of the airflow measurement system are the controller. So it's a KMC Conquest controller, either unitary or general purpose controller. Temperature sensors, mixed air temperature sensor, outside air, return air. Depending upon the size of mixing boxes you have, you might have a longer averaging sensor. You might have to snake it across a fan array or a particularly large fan, or you could use a probe style. Outside air temperature, return air, just common sensors. You can reutilize existing sensors if you have a digital ready piece of equipment or a packaged piece of equipment that you're applying the airflow measurement station on. Supply airflow sensors, we highly recommend our SSS 1014 or 1015 averaging sensors, just to give you an average of the airflow across that supply fan itself, and optional damper actuator, and also optional room indoor air quality sensor. So if you're looking to meet some sort of a demand control ventilation sequence, you can incorporate a local sensor. And I think Harold put it well earlier. This really sets you up to have effectively an economizer controller with some additional diagnostics, airflow measurement embedded on on your system. So from a controller standpoint, you have the choice of the unitary controller. We provide you on the 9311 version of the unitary controller an onboard differential pressure sensor. So again, less I/O that you need to take up on the controller itself. Otherwise, you could also use a general purpose controller with an external differential pressure sensor. Nice thing about using the general purpose controller is it sets you up really to control any type of equipment, anything that's complex, package, rooftop sort of situation, or penthouse type of air handler. And of course, the two different flavors of communication, MSTP or IP. And when you order the controller, it comes with the learn mode sequence pre-programmed, and it also comes with the inclinometer. I should probably back up here and point out that this ASHRAE 111, as we are producing the characterization curve, the standard dictates that you should have a 10-degree differential in temperature between return air and outside air.
10 degree or more.
10 degree or more. So that's one of the caveats for initiating the learn mode. But there's also the ability to work with a local balancer to manually create that characterization curve as well. So that wouldn't require the same differential in temperature.
And keep in mind that's just only to develop that characterization curve. After that curve is characterized, it no longer needs the temperature sensors. They're there for reference and recalibration maybe after a year or so. So we are not reading outdoor air based on the temperature formula. We're using that formula because it works and it's effective, as opposed to reading velocity at the intake. It is actually recommended by ASHRAE in the 111 standard to do it that way if you don't have good straight lines of ducts. So we're following those procedures, and they do work if you do them correctly. So once it's learned, Once you learn the whole thing, it is 100% dependent on the supply airflow station and the inclinometer.
So you could say, effectively we've got, as we're measuring or creating the curve, we're taking multiple readings, and that goes into the characterization table, and we're taking as the damper drives to full open, we're taking a lot more readings on the low end, and then as it steps up incrementally, we take readings at every 10% of degree, or full 10% full stroke, effectively is what we're taking and putting into the table.
And what we're storing in that table, sorry to keep,
Okay.
What we're storing in that table is the percentage of outside air. We're not storing a CFM value, we're storing a percentage of outside air. So percentage of the total. So now we're going to reference that percentage to the total that we're measuring accurately. That's the concept.
So just a couple of examples of where you would install the airflow measurement sensors. The inclinometer itself is, this is really the secret sauce, and this is where a lot of the, or all of the patents have been derived. Scott, you want to talk about which part of the technology is patented?
Yeah, measuring airflow by damper position and using the outdoor air formula, the mixed air formula, to create a table, and using that inclinometer or damper position sensor.
Yep.
That's exactly what we're doing. So the 50% open doesn't necessarily mean 50% of the airflow.
Yep.
No, so we are measuring that and storing those values in the table. So we're measuring it by. Are you guys familiar with the mixed air equation? The temperature. Yeah. So we need those mixed air temperature, return air temperature, outside air temperature, and we're verifying it by that, and developing the curve based on that. And by the way, developing those curves using that formula is and I own testing and balancing firm in Connecticut, own and operate. It's one of the largest in the state, but I'm here to admit that the way we're doing it here programmatically is far more accurate than how a balancer can produce these readings, because we're measuring them all at the same time. Now, time has a big effect on your measurements, because if you measure your supply air, you're doing that at one moment. If you measure your return air temperature, your outside air temperature, you're doing those all at different moments, and everything changes constantly. But when we're doing it this way, it's all at the same exact time. So that's what makes that temperature formula even that more accurate. So when we come to calibrate these, we expect a balancer to, if it is necessary to calibrate them, we expect the balancer to just only calibrate that supply airflow station. And that's it. And then the rest of it is going to be done by the temperature formula through the algorithm. And if the delta T is not there, then you can use the balancer to develop that curve by a 13-point calibration.
Just so you know, the transducer reads the higher velocities more accurately than it does at low velocities, so this is actually a pretty good way of doing it.
That's exactly right.
At the outdoor air intake with some device.
That's exactly right. And that's the downfall of most velocity sensing devices. You're measuring at a terrible environment. It's low velocity. It's in a bad weather environment, dust, debris, whatever. And it's inconsistent. When you're measuring it at the fan inlet, it's solid all the time. And when that thing moves, it's solid. You have high velocities, and the percentage is far more accurate, the readings.
So that inclinometer is also used during the commissioning process, essentially when we're creating that characterization curve. And in order to also create that curve, we need to take control of the damper, of the outside air damper. So ideally, we're looking for a modulating damper actuator. If you're using a jade economizer, might complicate things a little bit. You might have to take control of that economizer, or write to the economizer or pass that point through to the, figure out how you pass that point through to the actuator, or ideally you just rip the whole thing off and put on a KMC actuator. So the reason for taking control of the actuator is to essentially run at full stroke, and we're going to take measurements at each position of the damper, and then that is what effectively goes into our characterization table. And then, after the fact, if you're looking to achieve any type of demand control ventilation sequence, or just, proper control of the piece of equipment, you can leave, KMC actuator in place. If it has an existing actuator, then you can go through a couple different control modes that I'll talk about here to provide, pass control of the actuator back to the system. So how it works. Good catch. Yeah. I don't know. So whatever, Back to the Future might have something to say about that. But it measures outside air and return air by characterizing damper force. I think we've beaten this thing to death, all right? So I'm just going to keep going. Learn mode characterization, again, for anybody that's not, familiar with the ASHRAE 111 standard, the way that we set it up from the factory, you can either configure the learn mode when we are creating the characterization table remotely, so that you can do it manually whenever you see appropriate delta T, or we can configure it to automatically start when there is that 15-degree temperature differential between return air or outside air. It can run at a lower differential. You just get better readings and a much stronger correlation and a better characterization curve when you're following the standards here. So we recommend a couple of different times when to execute. Again, when you can maintain greater than 15 degrees delta T for a minimum of 2 hours. Because again, we're driving the damper full stroke, open and close, to create that characterization curve. So we need a little bit of time for all of the measurements to take. We recommend doing it at night because you don't see as much variation thermally from the sun. And we also don't recommend doing this when we're in the middle of a polar vortex, because you're going to open up your outside air dampers full, so you don't want to freeze up your coils.
Unless you had some provisions for that, glycol, or even running that water coil, running some flow through it. You got to pay attention to that stuff if you're going to do it in a freezing environment. And pressurization issues, we have to understand that when we're opening a damper 100%, it's going to affect, if you're in a very, very tight room, it can affect pressurization. So we just need to be smart about running that sequence, just like anything else. You guys are all control guys. You know that we can't just be sending dampers 100% open, 100% closed, and not paying attention to what's going on.
So touched on this a little bit, the different types of control modes pass through. This is effectively where the airflow measurement system, to its name, acts exclusively as an airflow measurement system. It just gives you feedback on the airflow and system performance. Or we give you the ability to control to a specific mixed air temperature. We can give you the ability to control to a specific outdoor air volume. What's cool about this is, if you need to see, we've seen a couple different regulations where, people are being forced to display what's your ventilation rate in the school system. Well, if you're using a KMC net sensor, you can completely configure that to show you what are your air changes per hour in the space and display that right there for everybody to see. And control for it, yep. Or the other option is to control for damper position. And then again, Tom, like you'd asked, different economizer sequences can be accomplished. Gonna take a little bit of programming and connect, but I'm sure you can handle it. So we do also provide a number of different faults embedded on the controller. There are Title 24 faults, sensor faults. So if we see stagnation in the temperature readings from the sensors, damper faults if we're sending a signal and we're not seeing any modulation, or if we're seeing the supply air fan ramp and we're not seeing the equivalent type of performance that we would expect from the damper. We have got a fault available for that as well. Outside air flow status faults and active control mode faults, position, mixed air, and outside air volume. Again, monitoring the actuator, monitoring all the temperature sensors, and monitoring the supply fan. So again, just a quick review here. We're providing accurate outdoor airflow measurement. We're compatible with nearly every piece of equipment. We feel that this gives our partners the ability to comply with nearly any type of indoor air quality regulation and policy, maximizing occupant wellness within the building. We're giving you increased performance data rather than having to buy an Ebtron sensor or install an Ebtron sensor for your outside air, return air, and mixed air. We give it to you all in one package. And we provide interoperability with any open building automation system via BACnet. And here we even spell out the fact that yes, you can do economizer control. Characterization routine, again, creating that table can be done locally or remotely. And just the fact that you don't have to go out and clean probes on an annual basis or have to reconfigure mechanical system just to get the parts installed, we feel is delivering a lower total cost of ownership. So I'm going to yield the clicker.
May I? So I just want to say that we've been developing this for almost 5 years now. So this isn't like a COVID thing. This all started to combat all of the issues that we have with typical thermal dispersion measurement on the outside air. So as a balancer and running a balancing firm, I've been balancing for 22 years. It has been this huge elephant in the room, this misconception of that people are trusting the thermal dispersion or velocity readings in the outdoor air intake completely. And I have to say the thermal dispersion is very accurate at measuring velocity, but we should not ever be measuring velocity in that environment. It just shouldn't happen. So here's some trends for the last a couple years now. After I've developed the semi-final product, we installed it in some pilot sites, and this is a really big office building in Connecticut that I was allowed to install in, and we had Ebtron and a Ruskin outdoor airflow measurement system that was calibrated and installed by third party. I had nothing to do with it, and I was there to install mine, monitor theirs, and compete and compare. So I was lucky enough to have that opportunity. So this is the same unit. The black line is demonstrating the damper position. I sent the damper position to 65 degrees. This is 0 to 90 degrees, but we configure it to 0 to 100%. But in this case, 65 degrees, I sent it up to 75 degrees, back down to about 5 degrees. And so this is the story. I kind of just did some stepping here. And what I want to point out is how erratic the velocity sensors are compared to the blue line, which is our airflow monitoring. Now we're only displaying in this graph the outdoor air because that's obviously the most important that we're trying to read. So this gold line is the standard. That is what I'm calling the standard, and that is that is the measurement of airflow by temperature while we have a good differential temperature. So it's the accurate reading. So that is what the airflow is delivering, no questions asked.
It's the reading that the balancer would produce.
That's right. And a good balancer. Yeah. Right. Yeah. So yes, this is the gold line is the standard, I'm calling it, and you're going to see that in a couple more slides. I've got a whole portfolio of these trends, and I've been studying forever. But I just want to point out here the green line is the Ruskin, the red line is the Ebtron, and we're already starting off measuring higher than normal for whatever reason that is, and they are erratic a little bit. And then you notice at the top, the Ruskin is above the Ebtron when we sent it to 75%. And when we sent it down to 5%, this is where it kind of gets interesting. The Ruskin doesn't know if it's 0 or 2000 CFM. The Ebtron thinks it's doing 6,000 CFM plus or minus, and we're just trucking right along at the right amount of CFM. We're right on top of, I'm pointing with my finger and I've got this. It's kind of, so, we're right on top of that standard. We're right there. And you can see, this curve here? That is the temperature sensors acclimating. Now, that's just there for reference, but I just want to show you guys that we're even faster after we learn this thing, that we're gonna give you an immediate airflow reading. Whereas even with the temperature mode, the temperature sequence, there's that time of acclimation that isn't even, it takes time to get to that actual reading. So it is quick and an accurate reading. What's more about this we talk about? That should be it. Oh yeah, I wanted to also show that if you notice up here, the Ruskin was above the Ebtron, and then when you come down here, the Ebtron is above the Ruskin for whatever reason. And I'm just trying to point out the inaccuracies, inconsistencies of measuring outdoor airflow by velocity of a terrible environment. All right, anybody tell me what's happening here? So this, I'm gonna spoil it for you, but this is a 4-hour period of rain. And this is what happens to thermal dispersion when it gets wet. Thermal dispersion sensors are based on heating an element, airflow blowing across them, and then determining velocity based on the resistance of that element. We are getting those elements wet in this scenario, and it's showing a velocity that appears to be higher than what's actually there because it's cooled down by the moisture. So if you can see let's see, we have a pretty good jump here, and this is like within a minute. So what is that, 9,000 CFM to 17,000 CFM jump? We're steady. We're the blue line, and the gold line is the standard. And I just want to point out too that moisture and rain, heavy driven rain, is also going to affect your temperature sensors. So that's why we have that those little bumps and stuff in there. But we're staying steady, and we're staying true, we're staying accurate, and nothing's going to stop it. Let's just keep going. Go ahead.
Do you know if the economizer was driving off those decisions, or was it steady state and the output of the actuator?
So this was, we were controlling to, I did have we were controlling to 5,500 CFM. You see, we just put, so it wasn't in an economizer. We were controlling this, manually operating these dampers to 5,500 CFM. Then we went up to 6,500. I was just messing around with that damper. And you can see, I was just sending in all different ways to try to see if I could get these things to come down to something reasonable, but that never happened.
You could show how those other sensors are wearing out your actuators, right?
Yeah, exactly. No, exactly.
Chasing
Right.
that erratic.
Right.
But that thermal dispersion, Ebtron is measuring the loss of heat over that thermistor as the air travels over it.
Exactly.
And the water is insulating that thermistor, so it does not lose any heat or doesn't measure that. So that's crazy.
Yeah. So I came across this by accident. I I knew where I wanted to be, but I didn't quite. And I knew a little bit about thermal dispersion, but I didn't realize it was going to be like this on a final product. You know, everything. You know, these expensive products that everybody's buying and holding hanging their hat on. You know, it just.
Right about their 3% accuracy too.
And I'm not going to put. You know what? I'm not going to doubt that 3% accuracy. Listen, if you had a good straight run of duct on the tail end of this air, if you had good conditions, you're going to make it right. And they are accurate. They are accurate to measure velocity. There is no question about that. I will not take that away from them. It's just the environment that we're putting them in. We cannot do that. It's like I said in the last class, it should be illegal, but.
Electronics and water doesn't work.
Right.
It's weird.
Yeah. So here's a demonstration of our learn mode, and this was in KMC headquarters in New Paris, Indiana. And this is what the learn mode looks like. And when you, oops, wrong button. So when you drive this damper open, obviously your outdoor air is going to start climbing. At the same time, your return air is going to start declining. And if you notice that it all makes sense, you know, you see a dip here, it's here too. You see an incline here, they're also inclining here. I mean, you're not really noticing it in this trend, but my point is it's going to match these exact. When your outside air goes up, your return air goes down, and it's going to make sense. So, like for the end user, you know, you go to a school and they're measuring outdoor airflow with thermal dispersion velocity sensor, and then you're measuring supply air. I've noticed more times than I can count how the outside air is measuring more than the supply air. Well, how is that even possible? You know, so that's when people start losing faith in that stuff and questioning it, and that's why this is kind of a big deal. You know, it's like you don't want to show that to your clients that you have. You know, people always question it. Why is the outside air more than the supply air? That doesn't make any sense. Ours will always make sense. It always makes sense. Whatever you have for the outside air and the return air will add up to your supply air. This is a different air handling unit at KMC headquarters, New Paris. And this is the VAVs modulating throughout the night. So they're calling and making. The VAVs are just doing what they got to do, and obviously there's just this trending of VAVs modulating. And what I'm pointing out here is that our supply air is here, return air is here, and here's our outside air. And we're just monitoring that outside air, and we had that damper set at a certain position. We're at 500 CFM, looks like somewhere around there. But you see this spike here, boom, this spike here, this spike here. So, you want to talk to them? Yeah. Okay. I might step on you a little bit, but we'll.
Of course.
Get to it.
So here's just some photos and just some generalized case studies. So when we'll conclude all of our events here at the end of the week, next step for us, we're going to start publishing all of this information on our website. We'll create a page specifically for the product. We'll include these case studies and our findings. This was a packaged rooftop unit. This is actually feeding our grinding room. It's variable and constant volume. We actually installed the pitot array in the duct in this instance rather than actually at the supply fan itself. We did the installation ourselves. Took about 4 man-hours. We were trending using total control and monitoring outside air. And of course, we're integrating to our existing backnet control system. Just a couple shots of the install itself. I know Scott wants to talk to you about this right here, this flapper.
Yeah, that's
So we made a trip up to Leroy Public Schools, or Leroy. That's a pretty rural site in mid-Michigan, and we've got an existing KMD controlled network there. We installed on some unit ventilators. We actually installed on 3 different unit ventilators in the classrooms and break rooms, both variable and constant volume. And we're measuring coil face velocity at the exit. It took us between 2.5 to 3 man hours per unit, just dependent upon like when we hit our stride, like we getting to know the pieces of equipment there. So we're monitoring outside air, and again integrating to an existing KMD backnet system. So here you can see, when we're measuring the velocity across these little squirrel cages, we put together a nice little pitot array or a manifold that we linked together and ran back to a unitary controller. We got to do an install at Denver Public Schools. This was completed in 1 day. It took us 6 man hours, spent a little bit more time, figuring out the mechanical layout of the system. Actually went on to a Daikin rooftop unit with powered exhaust. We installed a supply air duct pitot array. The installation was completed, again, by our partner Long, and we were trending data in Commander by the end of the day. Monitoring outside air, and the damper itself was being controlled by the Microtech controller. So after we took control of the damper to create the characterization table, we gave control of the actuator back to the Microtech controller. So here's a couple of pictures of that install. And this is where we had the pitot array installed.
The more probes you have, the better off the reading is going to be. But we have to just keep in mind that we're trying to measure it in an environment that's stable. If we had 1 probe in there, just 1, and we're measuring that velocity, and it was in a stable environment where there wasn't a whole lot of stuff going on, turbulence, and a tab contractor said you have 1,000 CFM going through there, and you calibrated to that, then it's gonna hold, because that's gonna change as you as your fan ramps up and down, or your VAVs open and close. It's a sensing point, and it's going to change proportionally. We would like to see as many points as possible to get the best reading. But like you asked before, do you have to have them both on each inlet of the fan? Yes, it's recommended. Do you have to? I'm telling you, as a balancer, it works because we're in such high velocity, we're in a stable environment. The measurement will be consistent.
Consistent.
Yeah. We're just looking for consistency, and once you can calibrate that, then you're ready to rock.
So if you haven't had a chance to visit the demo room, you can visit there later. We've created a couple of specific brackets for mounting our SSS, our averaging duct probes. So you can, out of the box, they're already going to give you a good average of the air velocity or the air flow that's going through your system. But we've tried to improve that experience a little bit from a installation and implementation standpoint. So just a little plug for the demo room. So by the end of the day, we were able to trend information coming from that piece of equipment in Commander. Again, looking at your supply airflow up here, your return airflow here, and your outside airflow at the bottom. And the other nice thing that we're able to do is automatically expose these fault detection diagnostics in a card. And it's a powerful piece of equipment, or a powerful tool to be able to do this in a day and say, like, here you go, here's your results. Oh, that should have been hidden. So we've also, this guy's going to say we're about 5 case studies in. 2 weeks ago, we were able to visit a school in Chicago, a part of Chicago Public Schools. They have a whole building air handler unit. I mean, this thing is, probably, like 10 foot by 10 foot is the mixing box or something along those lines, with multiple outdoor air and return air damper assemblies. We've got a couple pictures here coming up. We're measuring airflow at the supply air fan inlet. The installation was performed by Stanton Mechanical. It took about 5 man-hours. Again, we're training in Commander. What's really neat about this is it was integrated to an existing pneumatic control system. So we're taking control of those actuators from a digital perspective. We're giving Chicago Public Schools real airflow measurement data, and we're doing that all on an old pneumatic system that's probably been there since 60s, something along those lines. And we did actually have a third-party balancer come on site and produce a balancing report for us. Anything that you wanted to point out about that? I mean, I think that the real...
Pictures speak for themselves.
Yeah. So this is the school itself. It's just down the street from Wrigley Field on the north side of Chicago. And so here's a picture of the mixing box. So these are all of the outside air dampers. And you got your return air dampers here and here. So this is a view of that return air damper. Again, it just looks right out into the hallway. And there's leakage all throughout this room. I mean, there's gaps in the doors big enough to throw a cat through. And this is actually standing over here from along the wall of the outside air dampers and looking back. This is actually their filter bank. So when
Is all that like the 0% outdoor damper?
that's about right. I mean, we're gonna get to that. Hold on, Brian. Now, hold on, Brian. We'll get to it. But we installed the inclinometer right here on one of the outdoor air damper blades, and this right alongside these beautiful Ebtron airflow sensors. So I don't know how much PowerPoint presenting everybody in the room here does, but on the recent updates to Microsoft, when you start to put your pictures in, it'll give you suggestions for this is a picture of a family. This is a picture of a building. It thought that this thing was either was that? No. It thought it was a bicycle wheel, or or a mill. This is actually a gosh. What did we measure? Was it 90 inches?
The inlet's 7 foot across, and the actual fan blade is about 12 foot in diameter. So.
Yeah.
And this was awesome because so this whole air handler.
Yes, exactly.
They run in summer winter modes, so in the summer it's just 100% outside air for cooling, even though it's that day. And then in the winter they run it in mixed air. So they already had Ebtron across there that we could pump to. They already had mixed air transmitter that we could follow with our mixed air thermistors.
It's right there.
It was super cool installation that we could go ahead and
Yep. And so you see our air velocity sensors right there on the face. This is the panel for controlling. So we got actually got our pneumatic control system here that we're tapping into to take control of the actuator and get feedback from the system. And we're using a general purpose controller and a FlexStat. This is a part of the NERDS program, which we'll send out information on that for everybody later. But effectively, it's pneumatic equipment retrofits to DDC. NERDS.
So that control panel is probably about 20 feet farther back off the fan. So this installation, one of the reasons we used that was we wanted to remote mount that differential pressure sensor and not use the one integrated on the 9311. So you can't really see it in the picture, but all those POs that we installed, manifold together, remote differential pressure, run back to that control panel.
So the FlexStat, you're using that as your means of display whatever.
Actually, the FlexStat for CPS is part of the Fresh Air for All program, and they're retrofitting it. CPS has 1,100 buildings. 800 of them are still controlled pneumatically. So the combination of FlexStat to give a local schedule interface and some other pneumatic accessories, the FlexStat is really just a timekeeper for the building. So we had a convenient NSTP job.
that was 20 feet over there, we located all the stars and control over it from all on everything else.
But it does display the CFM values. Right.
Yeah. Here again, I think that's, we're using the same kind of pieces parts, but we pick the parts that best fit that installation because we can do that, build the best system for that battleship of an air handler.
Oh, so you want me to speak to this?
Yeah.
So this is interesting.
Press button.
This is the outdoor air in yellow, measured by us. And below that is the outdoor air measured by Ebtron. So the red and the blue were somewhere around 15,000 CFM, and those are 2 of the 3 outdoor air inlets. And then the other one was 22,000-ish CFM, so the sum of those 3 equal 50,000 CFM. Okay, well, we have 35,000 CFM of outside air, and that's because, and the difference between these two is because when the balancer went to calibrate this, he had no other choice, but this is what balancers would normally do. Send the outdoor air dampers to 100%, measure the supply, and say, that's what you have for outside air. They don't have any other choice, that's why they do it that way. Especially when you can't measure it with temperature, using the mixed air formula. That was what was done in this case, I guarantee it. And that's why they're showing 50,000 CFM of outside air and 49,000 CFM of supply air. It doesn't add up, but, and so we've discovered, and it's unfortunate for the facility, but we've discovered about 17,000 CFM of return air leakage, whether it was coming from the return air dampers or it was coming underneath the doors that were entering into the plenum. There was just a ton of leakage, and that's discovered by using that method in our system. And, huh?
A third.
Yeah.
A third.
So a third of all the air going through that fan was leaking.
Right. I mean, that's not good news for them, but it's reality, and yeah, free cooling. Yeah. And by the way, so think of how many Ebtrons were installed here. We have 3 on the outdoor air, 1 on the supply air, and there wasn't a return air measurement, right? Okay.
No return.
Okay, so put that in perspective of the cost. So we got $20,000 in parts. I don't know how many thousands of dollars in installation, and then you don't even have a return reading, and it's all BS anyways. So that's where we're at. So I also want to emphasize. I want to emphasize that this isn't we're telling you all about how this works, but it's not complicated. It's very simple. And long story short, so, airflow equals damper position. Once it's all done, damper position is equal to airflow by characterizing that curve. And that inclinometer is that sensitive to where we can accurately show that.
It also showed that it doesn't matter the quality of the damper because you've had.
Exactly. We're characterizing whatever garbage there is there.
Yeah, you can calibrate that door.
Exactly. Yep.
And at the end of the day, it's at least feedback. I mean, maybe you already know that the system's crap, but at least you got, verification.
Matter of fact, where the idea came from when we were developing was I was driving my truck one day and I'm like, I've got a tilt sensor in the truck that shows, how my angle. And I'm like, it's a Chevy.
So you sit still.
And I was just like, okay, well, what is it that does that? What's that technology? I didn't know anything about an inclinometer. And so I looked that up and that was like, huh. And then I discovered that inclinometer that went around, and that technology is used for machining and keeping machine tables perfectly flat and level, and so that's how sensitive and accurate that is, and that's why we're able to determine and come up with some accurate results. What's this? This is this was the difference of our SSS probes
Oh, this is the supply fan.
The supply fan.
Supply fan measurement. So we were like 52,500 average CFM. The Evtron that we were up against there was hovering at 49. But this was a slide because our balance report shows that our magnification factor, I think, was calibrated at 0.98, because the balancer said there is 52,220 CFM going through. So basically, without calibration, we were spot on. Because we're sensing that supply air in the proper location.
Right.
At the high velocities.
That's right.
Well, it's
That's
like
key.
They had a bar going to build that thing.
You're right.
So we had 4 pitos there. That was.
And keep in mind, those 4 pitos weren't spanning the entire, it wasn't a traverse, but it was verified. So then it was verified by a traverse that the balancer did. But it's consistent. It's consistent measurement, and that's what we're looking for. All right, Chicago Public Schools.
This is just information. This is the actual data that we got from the system. So the middle one I think is pretty interesting. You can point out the leakage that we're seeing off of that system.
Yep, so 17,500 CFM of return air when these dampers are 100% open. Okay, so the outside air is 100% open. Return air dampers are as closed as those pneumatics would allow them to go. And they were leaking by quite a bit, and all the leakage throughout the rest of the plenum.
Question for that. So if you went back and fixed the dampers, obviously this flagged you should replace these dampers. Do you
Relearn
mode?
Absolutely. Yep. And a lot of people ask, well, what if my damper was garbage or this or that? Well, your equipment needs to work. We expect it to work. It has to work. Just like any other.
That's just a great setup for that graphic that's over there on the right. So that yellow line that you see, that's our diagnostics. So as soon as we saw, that 15-degree delta in temperature.
This was actually a 6-degree delta when that line started operating. It was a 6-degree delta. And as the temperature differential got bigger, then we started getting right into where we are. So, and then it flatlined out. So as the formula works, that differential temperature gets larger. It's a more accurate measurement for our standard. We're not following that. We're just looking at that and comparing that. But it's available to see to make your checks.
So that's your outside airflow reading, and then the yellow that you see laid over right on, smack on it, right? That is our quality check to make sure that the system is performing as it should. And the red is based off of the table that was created the day before.
Any questions?
How do we get y'all to our engineer's office?
Great question, Harold.
None of that from me, right?
Yep, that's the next step.
Jesse is available to get on there.
Yep, and that's what we want to hear. We want to work.
As everybody heard in the presentations this morning, disruption, that kept going through my mind, and this is absolutely going to be one of those items. We are going to disrupt the outdoor airflow measurement world, and it's going to be hard because people trust these goldenrod Evtrons, and
So are you guys approaching these manufacturers with this stuff?
we will be. And
Do it for fluid. Because we have the same problem there too, we need 40 feet of straight pipe.
there's a standard that we didn't put up there, but 189 tells about the devices, and 111 is how those devices should work. ASHRAE 111 is the balancing standard. So, and it specifies there right in the standard that if you don't have a straight run of duct, you should be using the temperature formula to come up with those readings. There it is, yeah. Yeah, I mean, there's the standard word for word. Some components of system airflow are virtually impossible to measure with an anemometer or pitot tube. So why are we doing it, Why are we doing it?
Almighty up there.
people buy.
Right, exactly. They look nice.
It says gold. It's gotta be gold.
Right. And like I said, I am not bashing on the technology. It is absolutely 100% accurate and
You're just moving it.
yeah. It's yeah.
Well, and many of us have used this.
Perfect at 1 point.
What's that?
I've used this calculation forever.
Yeah, exactly. No, that's we use it as in balancing day to day. When we can.
I always look at it, we see a screenshot, and I just says, you're lying, that's not the right outside your
Right.
So engineers will appreciate that, it's trust data.
Yeah, and like I said before, and I've watched every Ebtron video on YouTube that I possibly could. I've done my homework with this. I know what their argument is going to be. They're talking about how a outdoor air temperature formula is inaccurate. I don't know how they're talking about that, but they're just saying because you should measure velocity directly. Well, I know for a fact, because I've done this for 22 years, that it is accurate if it's done properly. Now, doing it all at the same exact time is the key. Measuring all those points at the same time is the key to that formula working. If I'm measuring my outdoor air temperature now, in 15 minutes, that temperature could change in just a little bit. That's right. That's right. But if you get all of those points at one moment, including the supply airflow measurement, and you put them into that formula immediately, and you get that measurement, it's accurate. It's done. It's accurate. I will argue to the death about that.
And you know as well, I look at the response time of the instruments that you're using.
Right.
So the response, because I have to teach this to validation people all the time. They want to validate a vacuum or somebody's sensor on the wall, right? And they walk up there, some walk up there, I've seen them walk up there with $59 beers, and cobalt on it, and they're going to calibrate this $300 sensor I just installed, right? Yeah. But they walk up there with a handheld meter that's response curve is nowhere even on the same chart as a permanently installed sensor.
Right.
And they want to say they're going to calibrate the sensor. I said, no, all you're going to do is put a human error factor.
That's right.
That's all you're going to do.
That's absolutely right. Yeah.
And after about 20 years, they finally learn the next part. Unless you're going to do a wetback. Now, you do a wetback, I'll trust you all day long because the sensors is submerged. Right?
Mm-hmm.
If you're doing an air-to-air calibration, all you know is make the sensor read wrong.
Right.
So pressurized return fans.
Yeah. So yeah, those return fans. The sequence is always to track the supply fan. I mean, that is how I've always seen the sequence run. Sometimes it's based on pressurization for a relief fan. But as that damper opens, it's going through that sequence of all that, that if the supply fan moves up, the return fan is going to move up with it. If the outside air damper is opening, the building is pressurizing. It's doing that, and it's going to follow those, it's going to map those characteristics as it's doing it. And most of these we have had at Denver, we have relief fans, and I have studies with big old return fans, and it's right on. I have hours and days of charts and stuff that I've studied. You can ask my wife. She gets pretty irritated with me about.
I'm used to it now.
Yeah.
She's right here.
Yep.
He's always looking up.
Yeah.
Now it's on his phone, thanks to Eric.
Yeah. Right. So that's that. Any other questions? Any comments, Eric?
Check out the demo. Yep, contact AVP, we'll set it up. Let's do it.